Okay, so we're back to do one last lesson on connectivity. This is more of a vertex version, if you will. We have, so for, in the setting of kind of vertex disjoint paths, we have two theorems that we've centered on. There is a version with two sets. If I give you two subsets of vertices, A and B in a graph, either you have k vertex disjoint paths all starting in the first set and ending in the second, or you have an obvious reason why not, namely a separation of order less than k, with one set on the left and the other set on the right. We also have a version for a pair of vertices. If you give me two non-adjacent vertices, say u and v, then either there are k internally disjoint paths from u to v, that means paths from u to v that intersect only at those ends, or there's an obvious reason why not, namely there's a separation of order strictly less than k, so that u is strictly on the left and v is strictly on the right. So there we have either going between two sets or going between two vertices. We're going to be doing the mixed case here. And so let me start with the main definition. So this is a fan. If I give you a vertex of a graph G and a subset of vertices not containing that vertex, then a V comma A fan of size k is a collection of k paths and the rule is that each of these paths goes from the vertex V to the set A. Let me say all from so each pi is a path from V to a vertex in A. And if you look at any two of these paths that are distinct, they're going to intersect only at the vertex V. So each pi goes from V to A, and let's say for I not equal j, pi and pj intersect only at the vertex V. Okay. I mean, I could just, I'm writing that a little bit casually. I mean, V of pi intersect V of pj equals the singleton V. Anyway, so the picture here is just this. Here's V, here's my set A. So so this, what I've drawn in green here, this would be a V comma A fan of size 3. Right, so I have three paths. They all start at the vertex V, they all end at the set A, and they're completely disjoint except for the vertex V. So you should see this is a mixed version of what we had before, right? We have a version for paths that go between a pair of sets A and B. If I give you two vertices, we have a version for internally disjoint paths from one to the other. Now we're just mixing those two cases. We have one vertex and a set, and we want this structure. We want a whole bunch of paths that start at that vertex and end in this set, and they're going to be disjoint apart from that vertex V. So that's our fan. And yeah, again, we've seen a version of Menger. We have a nice if and only if condition for the presence of k vertex disjoint paths between a pair of sets. We also have a nice condition for between two vertices. Here, I'm just going to lean on those and prove an easy lemma that grants us the presence of this a suitable fan in a well-connected graph. Mainly because this is the setting in which we kind of want to use it. Anyway, so this is a VA fan. What we're going to be doing is proving that these fans exist under some reasonably sensible assumptions. I did a little bit more than this in the notes, but I'm just going to give you the one observation that I need because it's straight away. If I give you a k-connected graph G, and you form a new graph by adding a new vertex and joining it to at least k existing vertices. We form G plus from G by adding a new vertex, say W, and at least, and we join W to at least k vertices in G, and edges from W to at least k vertices of G, then G plus is also k connected. So this is, I'll just draw the picture here. So here's our graph G. This graph, by assumption, it is a k connected graph. I am forming the graph G plus by adding a new vertex. I am calling it W, and we're going to add edges between W and at least k vertices here. I'm just claiming that this new graph we formed here, G plus, is k connected. This is really straight away. Again, what does it mean to be k connected? You have to have two properties. Well, first you have to have at least k plus 1 vertices. So the graph G had k plus 1 vertices, so G plus certainly has k plus 1 vertices as well. The second property is, however you delete a set of fewer than k vertices, the resulting graph is connected. So if I take the graph G and I remove from it a set of fewer than k vertices, that resulting graph is connected. Well, if you want to take G plus and remove a set of vertices from it, well, if you remove the vertex W, now I'm just going to be deleting a smaller set of vertices from G. So if you remove a set of vertices, let me say that again. So if I remove a set of vertices from G plus with size less than k, if you remove W, then what's left, you're deleting fewer than k vertices from G, and that's going to leave you with a connected graph. If you don't want to delete the vertex W, well, then you're removing k vertices from our original graph G. We know that after you do that, you're left with a connected graph, and the vertex W is going to be joined to at least one of those vertices over there because W has at least k neighbors, and you're only deleting k vertices. You're deleting fewer than k vertices. So this operation of taking a k-connected graph and adding one new vertex joined to k, that is going to preserve the property of k connectivity. And that's the only thing we're going to need in our operation here. So here's our main lemma. If G, sorry about that. If G is k connected, and I give you a vertex and a set of size at least k, then G is going to contain a VA fan of size k. Right? So here there's some structure theorem you can get that would be an if and only if, but I'm giving you this lemma because this is sort of the form that we always want to use it. So I'm giving you a k-connected graph and giving you a vertex V and some subset A of vertices where the size of A is at least k. in that case, you are guaranteed the presence of a VA fan. So you're going to have these K paths that all start at your vertex V and go to the set A, and they are disjoint except for the vertex V. And the proof of this is really, really straightforward. What are we going to do? Well, I'm gonna go ahead and apply a version of Menger. Here's what I'll do. I will just take this graph G and I'm going to add a new vertex joined to A. So I'm going to form G plus by adding a vertex W and edges between W and every vertex in A. So because A has size at least K, this graph G plus is going to be K connected. And now my original vertex V and this new vertex W that I just added are non-adjacent. And but not that actually I don't even need that. But because G plus is K connected, I'm guaranteed K internally disjoint paths from V to W. Right, so, I should have drawn the picture. I really should have drawn the picture. So here's V, here's my set A, that's my graph G. We have formed this new graph G plus by adding a new vertex W and all of these edges. Now, in the graph G plus, we have found we found a family of K internally disjoint VW paths. So they look like this, and this, and this. And of course, if you just delete the vertex W from each of these paths, you're going to be left with a path in the original graph G that starts at V and ends at A. And because my original paths were internally disjoint, these new paths that we have will intersect only at the vertex V. So deleting W from each PI gives a VA fan of size K. Ooh, not a great box. As I indicated before, you want to see this fan lemma as a kind of hybrid version of what we had, of the earlier versions of Menger that we had before. So it follows from our earlier versions of Menger's theorem that if you have a K-connected graph and I give you any two sets of vertices of size at least K, then you have K vertex disjoint paths between them. It also follows that if I gave you two vertices, U and V, that you get K internally disjoint paths between them. Now we're just giving the hybrid version. So if you're K connected, you have one vertex V and a set of vertices A of size at least K, then you're guaranteed a fan. So these K K paths starting at V and ending at A, intersecting only at the vertex V. So this fan theorem, it's a hybrid version of what we had before. It's following all the same kind of logic. It is also quite useful. So the paths between two sets are nice, paths between two vertices are nice, and many times this fan is useful as well. I mean, you can think that if you're trying to find structures in your graph, having a vertex and many paths that start at that vertex and go to some set, that's a useful thing for finding structures. And we're going to give one nice example of that with our last theorem from this section on connectivity. So, so here's the theorem. So I'm going to give you a K-connected graph for K at least 2. And I'm going to give you a subset of vertices with size exactly K. And then the theorem's going to tell us that you're guaranteed the presence of a cycle that contains all those vertices. right? So that's quite nice. And also, you can see this as a generalization of something that we had before for two connectivity. So you remember that if I give you a graph that's two connected, then for any two vertices, you're guaranteed a cycle that contains those two. Now I'm saying if your graph is three connected, then you have a cycle through any triple of vertices. If you're four connected, you have a cycle through any four, and on and on. So yeah, so a very nice property here. And the proof is very simple. It's a very straightforward application of this fan lemma, and you really see in the guts of this how to possibly use this. So I like this. I like this theorem sort of maybe more for the proof than for the actual statement itself. But it's, anyway, nice fact. So basically what I'm going to show you here is a simple way to use a fan to take a cycle that contains some but not all vertices in X and keep all the ones that you've found, but add one more if you don't yet have all of them. Now, just for the sake of sort of cleanliness, I'm going to operate by contradiction. So what I'm going to do is I'm going to choose a cycle C that contains as many vertices of X as we can. So I want to maximize the number of vertices that are in C and in X. And I'm going to suppose for a contradiction that we don't have all of them. Okay, and let me go ahead and draw a picture. So, okay, so let's. Okay. So here's my cycle C. Let's be Christmassy. So we'll. So what I'm going to do here. X is going to be the set of these red vertices here. And so my cycle C is containing some of these vertices in X, and in general it's containing some other vertices. But there's at least one vertex out here, say V, that is in my set X but not contained in my cycle, right? So, I'm changing color green for no reason. So I'm supposing for a contradiction X is not completely contained in the vertex set of C, so that means I can choose some vertex that's in X but not in my cycle. So there it is. There's that vertex V. I chose a cycle C containing as much of X as I could. I got some but not all. And what we're now going to do is we're now going to show that that if there is So we're now going to lean on the fact that the graph is K-connected and our fan lemma to show how you can very easily take this cycle and find a use the fan lemma to construct a better cycle. I think I wrote this slightly differently in the notes. I'm going to I'm going to do it a little bit differently here than I did there. The argument is more or less the same. I'm a little quicker in the notes than I sort of feel like doing right now. So I'm going to split into two cases. So first I'm going to consider the case where you have at least K vertices in this cycle C. This is the serious case. This is the harder part. I think once you see this case, the other one gets easy. So here's what I'm going to do. I have a K-connected graph. I've got a single vertex V, and I've now got this cycle, but the vertex set of that cycle is a set of size at least K. By the fan lemma, I can choose a fan between that vertex V and this vertex set of my cycle C. So what we will do is choose a V, V of C fan of size K. And now I want to basically draw that picture. Now, what you'll see here is, well, I've got my cycle C, and there's some vertices in X that are on my cycle, right? Those vertices in X I really care about. I don't want to lose those, right? What I want to do in this process is just find a cycle that contains all the vertices in X that we already had on C, but also picks up this vertex V. So all of those red vertices that I have drawn on my cycle down here, I want to keep those. I just want to add the vertex V. Now, those red vertices that are on my cycle, those vertices in X that lie in my cycle, they're dividing this cycle up into intervals, right? You can see here I'm thinking of this as one interval, and then this is another interval, and so on, right? So because I have at most k minus 1 vertices in X that lie on my cycle, remember the set X has size k, and the vertex V is in X but is outside, is not on the cycle. So there are at most k minus 1 of these vertices that are in X that do lie on the cycle. So that means that in relative to this picture that I'm drawing, my cycle is going to get chopped up into k minus 1 or fewer intervals. Now, we have a fan of size k, right? We've got these k paths that come from V down. They're allowed to end at the vertices in X or not. But the key feature here is, well, I've only got k minus 1 intervals here, and I've got k paths coming down. And that means 2 of these paths have to come down in the same interval. I've drawn that. I've drawn that right away here. I'm just trying to find a new color. I've used all of the colors. Okay, how can that be? I will just use brown. So you can see I've drawn this path and this path coming down in the same interval. As soon as you have those 2 paths coming down in the same interval, you have a very simple way of rerouting your cycle to pick up the vertex V. Namely, you walk around the cycle like so, but then you just replace this little part of this interval with a path up to V and a path down. So the idea here is I can choose a V to V of C fan of size k. Now, using that fan together with the cycle C, we can form a better cycle C prime that contains all the vertices in X plus also the vertex V. So this fan, I mean, I'm not writing this very precisely, but this fan together with C contains a cycle that has all the vertices that you had before that were in the set X, but also has the vertex V, and that's a contradiction. That's a better cycle than the cycle that we had C. So this means that this contradiction is telling us that the cycle that we found actually had better contain every vertex in X, or we were done. So again, the idea here is we're trying to prove that you can find a cycle through any k vertices. So we're given a set X of size k. We found the best cycle that we could. If it missed some vertex V and that cycle has size at least k, then, well, the vertices in X that do lie on the cycle chop up the cycle into k minus 1 intervals. Because I can choose a V to V of C fan of size k, I'm going to be guaranteed 2 paths that start at the vertex V and have their other ends in the same interval. And then that allows me just a very simple rerouting to improve my cycle, and that's a contradiction. Now, there's one other case here, which is when the V of C is less than k. Now, if the vertex set of the cycle has size less than k, well, now you can't find a V to V of C fan of size k because there are too few vertices on the cycle. But that's not really a problem. You can, in that case, just you can find a fan that goes from V to every vertex on the cycle. So in this case, G contains a V comma V of C fan of size the number of vertices of C. So in other words, we get a fan that has a property. So every path is going to start at the vertex V, but you have one path ending at each different vertex on the cycle. And so then you can find a new. So then you can just take two consecutive vertices on your cycle, and you can walk around the whole cycle and replace that one edge between them with the path out to V and the path back. And that again is going to get you a cycle. This new cycle that you found is going to contain all of the vertices in the original cycle C, but also pick up the additional vertex V. And that's an improvement that gives us a contradiction. So this follows by the same argument, and I'm just going to call that done. I'm sorry, I'm not writing something a little bit bigger or clearer, but this argument you should be able to see if you just kind of think this thing through and take a moment. Again, the fan lemma is the driver here. It's a really nice lemma that gives us this very sensible and very usable structure. So if you have a k-connected graph, you have any two sets of size at least k, you're guaranteed k vertex disjoint paths between them. I give you any two vertices, you're guaranteed k internally disjoint paths between them. If I give you a vertex V and a set of k or more vertices disjoint from that vertex V, you're guaranteed a VA fan of size k. And so those are three very similar structures, and all very useful for uncovering a useful structure within a graph. And and that's going to do it for our chapter on connectivity. So I will stop there.